Okay. Hi, everyone, and welcome to today's webinar, Calibration and Validation of Micromodels, hosted by ITE ANZ, Australia and New Zealand section of the Institute of Transportation Engineers. Thank you for taking time out and being here today. Before we begin, I'd like to make an acknowledgement of the country on behalf of ITE and pay our respects to the traditional custodians of the land of Australia and New Zealand, in which this webinar is held on. ITE acknowledges the Australian Aboriginal and Torres Strait Islander peoples as the first inhabitants of the nation and the traditional custodians of the lands where we live, learn, and work. We pay our respects to elders past, present, and emerging. ITE acknowledges any Aboriginal and Torres Strait Islander peoples who are with us in today's event. ITE also acknowledges and respects the Treaty of Waitangi and Maori as the original people of Aotearoa, New Zealand. We acknowledge people of Maori descent who are with us in today's event. ITE ANZ is a section of the Institute of Transportation Engineers based in Australia and New Zealand. As an overview, the ITE ANZ is an international membership association of transport professionals who work to improve mobility and safety for all transportation system users.
There was a meeting, and that meeting was...
sorry, can you please mute yourself? Thank you. Well, ITE ANZ is an international membership association of transport professionals who work to improve mobility and safety for all transportation system users and help build smart and livable communities. On behalf of ITE, I also would like to acknowledge our generous sponsors who, by their financial support, not only support the operations of ITE ANZ, but also share in our ethos to improve transport and create a better world. We are proud to have Austraffic as our platinum sponsor, sponsoring our student award. We are proud to have Traffic Words sponsoring our President's Dinner and Postgraduate Award. We are proud to have Sidra Solutions sponsoring the annual breakfast. We are proud to have RIACV Club. And also, we would like to acknowledge our corporate sponsors, Arab and O'Brien Traffic. ITE ANZ are always open to partnering with you and your respective companies. So if your company is interested in supporting the work of the ITE ANZ and partnering as a leader in the field of transport, please get in touch for an obligation-free conversation to find out more. So we are currently taking we are currently having the YIT Road to Recovery Award. So the nominations for the third round are open. So if you want to nominate someone or nominate yourself, please use the QR code. Since ITE ANZ is committed to promote professional development of its members and the transport industry community in general by supporting and encouraging education, stimulating research, and developing public awareness, in this regard, we would like to hear from you topics of your interest that you would like to see in a future ITE ANZ webinar or seminar. So we will send a link so you can write the topic ideas. A special thanks to the organizing committee to make this webinar possible: Danielle, David, Sarah, Matt, and Rue. So just some basic housekeeping notes before we kickstart. Please keep your microphones on mute. We won't be taking questions during the presentation. However, if you would like to ask a question, please feel free to drop it into the chat at any time during the presentation, and they will be addressed at the end in a dedicated Q&A session. We'll be taking a survey at the end of the webinar, and we kindly appreciate if you can take 2 minutes of your time to fill out the survey. The link will be dropped on the chat later. So without further ado, it gives me great pleasure to open this webinar and introduce our first speaker, Rebecca Strahan. Rebecca is an associate director at GTA Consultants, now Stantec, with 17 years of experience in transport engineering within Australia and the UK. Rebecca has a specialty in the operational performance analysis of networks with a focus on traffic signal and intersection optimization and design. She is highly skilled user of Sidra and undertakes and reviews models from all GTA offices and on behalf of clients such as Transport of New South Wales, Fairfield City Council. Rebecca also provides technical advice to LeanSig, vSim, and IMSUM modeling projects. So over to you, Rebecca.
Thanks very much for that, Christian. I will just try and share my screen now for you.
Yeah, now you will be able to share.
I think this should come through.
Yeah, perfect.
Fantastic. Okay, look, thanks very much for the opportunity to present today. For those that are listening, the presentation is broken into 3 sections with the 3 speakers. And the first content that I'll be discussing is a little bit about what is calibration and validation of models, the purpose, but more broadly how it fits into the modelling process. And then our next speakers will talk on more specifics. So in order to understand the calibration and validation process, we really have to make sure we understand the purpose of the modelling that we're undertaking. So when we're undertaking a model, we're using a tool to investigate what could potentially occur on the road transport network under a variety of scenarios. So realistically, we're understanding the cause and the effect of change. So when we're looking at that, we have to understand why we're undertaking the modelling, what we're trying to achieve or demonstrate, and then how can we demonstrate that in a useful manner for our clients. And understanding the purpose of the model really changes and forms the way we look to our model for understanding model extents and the data collection. And that has a real imperative process in forming how easy or difficult the calibration and validation process is. So for those that are undertaking modelling in the past, it will be no surprise that we often look at undertaking models for assessing land use changes, such as major shopping centre expansions or new developments for residential areas or industrial areas. We might evaluate the differences in options for road network changes or something on a smaller impact of what's a preferred solution to an intersection upgrade to address a road safety problem. We can also use models to understand what the likely impacts of policy changes are, and that might be something such as managed motorways or different prioritisation of modes through the road network. Sorry, screen has just frozen. Okay. So that's the purpose. The what is probably a bit more of the specifics that we're looking for, and these are what guides the modelling results, and also the validation as to understanding what net differences are. So we can be looking at some specifics such as, is there spare capacity in the road network to accommodate demands, whether there's a cost benefit of proposed road network changes, or whether in the case of microsimulation and route network modelling, whether changes will alter the route choices of users. And how we demonstrate them, which really comes back to how we're conveying a message to our clients, can be through demands and route choices, travel distance, travel delays, travel times or delays at an intersection, queues, capacity parameters such as degree of saturation or level of service, and signal timing and operation. Now, all of those elements I've just listed form part of the base model process and then into the calibration and validation. Now, base model process, there's a lot of documents around, particularly most road network and agencies have their own modelling guidelines which detail the process, and also more recently Austroads have released a document on the management of traffic modelling processes and applications which investigates base models. The general process is the same regardless, it's just the metrics coming out of it that are the nuances. So after developing a model, and we need to identify the purpose, and we get into this circulatory process of calibration and validation till we get to a point where we can demonstrate.
You didn't even fucking do it, Matt. So.
Sorry. We go through a circulatory process until a point where we can demonstrate that our model is representing the existing conditions. And that's the key point that we're trying to do, is set a standard before we get through to future scenarios so that we can identify the net change. So what is calibration? So model calibration involves adjusting specific parameters to a model or network and the inputs to replicate the existing conditions. And there's three main components, regardless of the model's software package that you've chosen to use. So we have our network verification, such as road geometry and configuration. We have our route choice, which still exists for Sidra and Linsig models, where you have small networks. It just doesn't necessarily form on an origin destination basis at all times. And then we have our demand calibration. And as you can see, this is the largest section and often the most complex to calibrate because of driver behaviour patterns. So when we get to the specifics, and these are all detailed in user manuals for the various software packages and the road agencies guidelines, there's a number of key elements for model calibration. I would recommend that all of these elements actually get considered when you're reviewing and developing a model, but by consideration, we don't mean that they always have to be changed. The main thing is to make sure whether default parameters built into the modelling software packages are appropriate for use under your circumstances. A number of these would be considered by most as general base inputs that you have to provide, and that would be your road geometry, lane lengths, lane numbers, configuration, intersection control, and your demands. And by demands, that can be traffic, general traffic, and the vehicle composition, but it can also extend to public transport modes, pedestrians and cyclists. So once you've got that, the question is, well, okay, what do we do with the model? And this is the step that I think, particularly in small models of very small networks or isolated intersections or singular intersections, sorry, this is the part that often gets let down in the process because we don't often go to the full extent of demonstrating what is a validated model, and that is one that represents the existing conditions. So when we're looking at validation, there's a number of parameters that we can confirm, and it's really important that these elements are compared against your existing surveys, knowledge of the site, in order to show that the model is representing the existing conditions, and therefore your future model is actually going to limit the risk associated with providing erroneous results. So for models that allow route choice, there's two primary validation performance measures, and these are documented in the road agency guidelines, and that's predominantly the volume, the traffic volumes and the travel times. So for traffic volumes, we have two major parameters which are used, and the first one is the GEH, and that's a statistic used to compare modelled and observed volumes. Because we're providing inputs in broader surrounds or origin destinations, it's how the model is allowing the route choice to occur within the intersections, and then does that represent the existing conditions within relevant tolerances to say that the model is fit for purpose. For route choice models, travel times can also be a very important measure to demonstrate if you've got enough congestion in the network, if there's situations like your traffic signal timings providing the right amount of green time, or more to the point, inhibiting traffic flow where necessary. And for this reason, the different road networks have different criteria as to what is considered a validated model. And for this, where a number of you might be working for consultancies that cover projects from around Australia, it's always important to refer back to the relevant road networks guidelines. And you can see here the difference. So New South Wales might have an average model time requirement of 15% of vehicles within 1 minute of your surveys, whereas Victoria is 10% for the whole route. So it can make a significant difference, and this can actually make a really big change to how many iterations you need to go through in the modelling process to recalibrate and reproduce results that will meet these criteria. But in addition to those two parameters, and these are probably some of the more important ones when we're talking about smaller models, is that there's other validation measures, and that is often the intersection capacity, where for existing conditions models, we need to see a degree of saturation less than 1, so a ratio of demand over capacity. Queue lengths are often a very good performance measure, because everyone that's involved in the road network can identify where they see cars queuing to, or you can conduct detailed surveys in order to validate against it. We use items such as Google Traffic to understand where slow vehicle speeds are or queuing, and so that's another really important one to use. And depending on your project itself and the data you've collected at the time, stop line delays for roundabouts and T intersections can be a really good performance metric, as well as things like traffic signal timing for cycle length and phase splits, and also lane utilisation. Now, it can be difficult particularly when you're starting up in it as a modeller, to understand which performance measures to validate. And so that a number of the modelling guidelines produced by the road authorities actually indicates which categories of validation they consider as required, or even some say a preference to exploring them depending on the model. But the main thing is to come back. I'd implore you all to come back at all times to understanding the purpose, and really think about what it is that your client is aiming for out of this modelling process. Now, clients can be internal clients. If you're in a modelling team, you could be working with designers, town planners, but also your external clients such as councils and road authorities. And so coming back to understanding, why are we modelling this? And the final one is, how is the model going to be used going forward, is actually where I would say that the real measurements of validation come out to be clear as to what you're trying to demonstrate. So for a small intersection, validation of a single site, and the purpose of it might be to assess just likely increasing queue lengths. That might be okay to do a net difference comparison of where input demands from your traffic demands and your road geometry are adequate to enable that to occur. But when your client needs a specific outcome, they might have a very detailed brief. And I'll just show an example of one network model where we had a brief to provide calibrated existing conditions models for a broad congested network. So instantly the amount of data collected increases to understand what are the existing conditions road networks. And we undertook classified turning movement counts, Q surveys, SCATS detector counts, and SCATS traffic signal operation data. We were able to input elements for our calibration as the road geometry and demands and phasing and offsets. And under initial process, this might give you results that are reflective of your existing conditions. And to test that, we were able to compare that the modelled traffic signal data matched the SCATS data. So from our side, that was an easy one. But in this process, we found that our degree of saturation was over 1 for existing conditions. So this represents our first cycle back into data to calibration, processing to work out where the differences are, and come back to check the validation. Now, through that process, we were checking lane utilisation. And for this particular site, we were able to find that vehicles are using our bus lanes. So there's lots of processes that you can go through with the models to understand whether you are representing existing conditions that wouldn't be expected to be the norm. And following that process, the final calibration that the client was after, validation, sorry, that our client was after was average queue lengths. So after probably 6 iterations, we were able to get to the point of demonstrating that we had a validated model. Now, the validation of a model is, to the modeler itself or whoever's undertaking it, is only the first step, because the next step is to always convey this message back to our clients or create documentation in-house to demonstrate the processes have been undertaken. For this reason, we really need to understand who is the audience, what is it that they need to know, and what proof it is that they need. So the modelling, calibration and validation process required by road authorities is detailed quite well and in a lot of detail in their operation guidelines. But just for the purpose of today, before we go on to our next speakers, I just want to highlight that often as an industry, it's in the small model reports that we can potentially let ourselves down, especially in the situation of a transport impact assessment where there is a large number of details and issues being considered. As undertaking peer reviews for clients, both internal to GTA and external, we can see situations where the structure of the modelling section, we get our objective and our purpose. We'll have a couple of statements about the data collected and identification of a peak period. We'll go straight into the modelling process that says we've undertaken our existing conditions model and here's the results. And often I'll see statements, and I've been guilty of applying them in the past as well, where we say statements past the results to say the calibrated model shows, or the analysis shows that the intersection operates well with satisfactory queues and delays, but there's no quantifiable statements. And this is the real thing that's difficult for clients to understand, to demonstrate, and also to satisfy to themselves that the modelling is actually appropriate and fit for purpose before they proceed with the future scenarios. So look, to wrap it up from the introduction point of today's presentation, when you are writing your reports, I just suggest, if you can, of really try and get those quantifiable statements and include and document the hard work that you've undertaken, such as comparing your SCATS phase times against a model if you're dealing with a signalised intersection, or demonstrate that you've actually compared your modelled queue results to your surveyed results. And finally, if you have had an issue with calibration and demonstrating that your existing conditions have a degree of saturation under 1 for stop line counts, that you quantify it, acknowledge it, and then identify what it is that you've done to improve that. Now, the identification doesn't have to go in the body of reports, but it can be appendix and just enough so that if somebody's peer reviewing, or down the line, if your own colleagues pick up a model, they know the steps that have been involved, and it gives everybody more confidence in the process undertaken. So look, sorry, that was just a very high overview of the calibration and validation techniques and process and the purpose, because I know a lot of you will be more interested in what our next two speakers have to say about the nuances of using their particular software packages. So Christian, I will pass back to you. Thank you. I will just stop this. Has that stopped, Christian?
Thank you. Yeah, thank you very much. Can you hear me?
Yes, all good.
Okay. So thank you very much, Rebecca. For our second presentation, now we have Mark Beasley. So let me please. So Mark is a director of Axelic and Associates, trading as Sidra Solutions, and has been working there with Ramik Axelic since the formation of the company in 1999. He had previously worked at the Australian Road Research Board. Mark's current roles at Sidra Solutions include software development, delivery, and training and user support. Over to you, Mark.
Okay, thank you, Christian. I'll see if I can share my screen. Share. So hopefully, all right, hopefully you're seeing that. I'm sure someone will tell me if you're not. Thank you to Rebecca. That was quite an interesting introduction, and I'll now spend the next 20 minutes or so speaking specifically about micro-analytical models. Now, when we say that, obviously, you're aware oops, I was not meant to do that. Sorry, just let me restart. I don't know why it's sorry, some reason went to the last slide. I do have a few more than 2 slides to show you. I'm going to talk from the perspective of a lane-based microanalytical model. Obviously, Sidra intersection is that type of model. And these sort of models work with key parameters, which I'll talk a lot about. An example of that is the saturation flow, which is a parameter, for example, that's not a direct input into a simulation model. So it is important to understand the types of models we're talking about. Rebecca referred to some of the guidelines and reports around. We had looked at a recent Austroads report that discussed the model classifications. We did a critique of it, and I would welcome you to download this report from our website at sidrasolutions.com, and you could read in that what we've said in terms of how we think models should be classified. Today I'm going to discuss a lot of the nuts and bolts. So firstly, you need to consider what measure you're using as a basis for your calibration. I'll talk about some of the key model calibration parameters you'll need to consider. I'll mention some of the pitfalls that might occur. I'll spend a little while talking about networks which present challenges with modelling, and I'll just get a little bit of detail about an iterative method. Rebecca already touched on this topic, just to indicate to you the complication of it. Now, the first thing to consider is what is going to be the basis of your calibration. Now, here's a few of the typical sorts of things you might collect. Q's very popular. You might have surveyed capacity values. If you've counted at the stop line in oversaturated persistent queuing conditions, you'll have a capacity value, which might be valuable to you to use for calibration. You might do a saturation flow survey. You might look at SCATS MF values, but I'll mention about those. SCATS MF is not saturation flow. I'll talk a bit about that. Or you might have done gap acceptance survey, travel time survey, floating car, travel delay. There's a lot of different sorts of surveys you could do, but in the end, what you want to do is to get your model results to match up what you observed. I'm not going to talk about different results from different models. That's really a different topic we could probably have another seminar about. We offer various spreadsheets. You could download these from our website to help you survey, say, saturation flows, back of queues, and you might go out and do that. But let's just talk about some more specifics. As an example, you might have gone and surveyed queue lengths. That's all very nice. And probably one of the most popular things we get asked about is matching CIDRA's queue outputs to what was surveyed. You need to consider the different queue definitions that can be output from the software, but also whether that matches up what you've surveyed, and then whether you're actually looking at average or percentile queue values. A lot of discussion about that as well. So what I'll do is talk a little bit about queues, as I say, that being a popular thing to survey, and where you might go wrong. You need to look at the queue that you actually surveyed. Here's a diagram showing how queue signals would build up during the red time. Vehicles arrive, the signals turn green at this point. Now, just let me see if I can do a better pointer for you here. So at this point, the signals turn green. Now, if I go down there, I've got a number of vehicles that have arrived that form a queue at that time. But although the queue has started to discharge, more vehicles may arrive at the back of queue. So what we call the back of queue occurs sometime after the start of green. Of course, that makes it difficult to survey, difficult to observe. So you may find queue at start of green is an easier one to observe, but make sure you're not comparing back of queue output from software to queue at start of green that you surveyed. I'll also mention the cycle average queue. You can measure the queue length, say, every 10 seconds and just do that through the survey period. Of course, that may include 0 queues, and for that reason, the cycle average queue is generally significantly less than the other back or start of green queues that you might be observing. Cycle average queue also has a relation to the delay times the flow rate, gives you cycle average queue. So in fact, that also becomes a delay survey method. So first thing is to work out what queue you've surveyed and make sure that's what you're looking at from the software. Just to illustrate the difference between cycle average queue and back of queue, you can see in this particular signal example that in fact it was about 2.6. So cycle average queue usually a lot less. You might also do a saturation flow survey, and the survey method in the spreadsheet I mentioned works like this. It has a first interval of 10 seconds and so on. It comes with instructions. The important thing to understand about SCATS MF is that it is counted over the full phase time. So SCATS MF value, because it includes a count during the intergreen, so the yellow plus the all red, will by definition be a lower value than the saturation flow. CIDRA can produce outputs of SCATS MF estimates, but they do depend on the timings, so you need to be careful not to necessarily assume the estimated MF is a good measure. SCATS doesn't tell us the signal timings that were in force when it collected the MF value. So that's another thing you might survey, but SCATS MF, as I say, be a bit wary. And I'll also emphasise, don't use SCATS MF as input for saturation flows. There are some draft guidelines that are talking about doing that. They are not the same thing, and you won't expect to get the same values. You won't expect to get a good estimate of capacity. If you use SCATS MF as a saturation flow, you're likely to seriously underestimate capacity, and therefore your queue delay predictions and so on will be wrong. Now, our recommendation, once you've done your surveying, you'll need to adjust parameters in the software. That really depends on the type of intersection that you're modelling as to which parameter we recommend that you adjust. For signals, the saturation flow rate is the key parameter. Either the basic saturation flow per lane or an area type can apply per leg. For roundabout sign control, the gap acceptance processes, the critical gap and follow-up headway are the key parameters, but we have adjustments in the program called environment factor, model calibration factor. For roundabouts, those are the ones to set. For sign control, the base values of critical gap, follow-up headway before the program adjusts them. Now, the software will adjust the base values, and that's why we recommend that you specify base values, allow the program adjustments to take place, and that will mean that when you're modelling perhaps other conditions, future flows and so on, that the program adjustments will still apply. We never recommend overriding the program estimate totally by giving specific input like a final saturation flow value. We do allow that sort of input, but once you've fixed something like that, there's no opportunity for the software to adjust it with other conditions that might change. For example, at sign control, if you add lanes or remove lanes on the major road, that would affect the adjustments to the gap acceptance parameters. If you force a specific measured set into SIDRA and you don't allow adjustment, then geometric changes may not be applied, and your future estimate for that reason might not be a good one. The queue space per vehicle, I'll mention heavy vehicles in a minute as well. These are important parameters. They affect saturation headways, so hence saturation flow rate or follow-up headway at gap acceptance, and also, of course, affect the queue estimates, which go into short lane capacity and blockage in networks and so on. Just an example of what you might do in SIDRA, you have measured a saturation flow of 1931 in this example. The program estimated 1864. Rather than forcing 1931 as a specific value, we would recommend that you find the ratio and use that ratio to adjust the input of basic saturation flow. Other things that are important to consider when you're surveying your intersection and therefore wanting to put inputs into the software, lane utilisation, Rebecca mentioned this, very important. Lane-based surveys, of course, recommended for that reason. Effects of heavy vehicles, there are several parameters in the software related to heavy vehicles that should be considered. We don't recommend moving your demand flows into calculating them into PCU values. We recommend inputting the volumes directly using various parameters in the program to make the adjustments for heavy vehicles. Of course, effects of pedestrians are important as well. Things like time loss for left turning vehicles with conflicting PEDs. And you also need to look at the signal timings. Again, Rebecca mentioned this. If you're calculating the signal timings, do they reflect what was applying in practice, or you may choose to input those. Coordination effects. If you don't take coordination effects into account, perhaps SIDRA has estimated specific queue or delay value based on random arrivals, but if you've got good coordination, you might be observing much shorter queues, as an example. Now, when you get into these adjustments, one thing or many things to watch out for, but the first one are the saturation flow values that you calculated with your adjustments sensible. If I saw a saturation flow input of 4,000, I'd be asking where that came from. Probably there are other effects. Maybe you've got vehicles creating an extra lane, even though the lane was not marked. That might give you apparently a much higher capacity. You need to work out why you're using a very high value. Again, a very low value. If you've got a saturation flow to do your calibration, you've ended up with a sat flow value of a few hundred. There's probably something else going on. So question them if they're outside a reasonable range. Same thing for critical gap follow-up headway. If you've had to give a critical gap of less than 2 seconds and follow-up headway of 1 second to match the capacity, there's probably something else going on that you haven't accounted in your model. I mentioned before, we don't recommend turning off the program adjustments to these basic parameters. Don't just input a value and say this is it, because when you look at other flow periods, future flows, perhaps geometric changes, the effects of those won't be applied if you've turned off these program adjustments. We also don't recommend that you simply directly adjust the capacity estimate from SIDRA. That capacity is an end result. There is a capacity adjustment. We sometimes see it misused. That is not the way to calibrate the model. It's like looking at the end result and just making it fit what you want. So again, don't do that. Networks present challenges to us because of number of factors like capacity reduction due to downstream blockage. There's a picture here that we took in Sydney a few years ago. Green signal, queues as far as you can see. The vehicles are not able to utilise that green. The capacity is adjusted down by the model to compensate for that. Of course, if there's upstream demand exceeding capacity, we don't allow the vehicles beyond capacity to proceed downstream, so demand may appear to be reduced upstream. These are network effects that come in. It does make it harder to set up your model in a network, but you need to think about all these things. Surveying queue lengths in a network is difficult because if it's all full, well, the queue you observe is the entire distance from the downstream stop line to the upstream departure point of the intersection, but that's a physical constraint. Of course, any demand that couldn't get in there is being stored upstream, causing queuing up there. So you do need to look at your network as a whole if these sort of effects are happening. Other things that will affect networks a lot are driver exit lane choice. So like the left turner could go into the nearest lane, but they may have a downstream intention to turn right, so they'll turn from lane 1, they'll go immediately into the right lane because they want to make a right turn. So these effects come into networks as well. Not knowing the full OD demand for the network, that can be quite difficult. You may need to look at traffic assignment software to try and get those estimates. Of course, if conditions are oversaturated in your network or in parts of your network, it may be very difficult to actually know what the full demand flow is as well. And of course, that demand flow is what will affect your performance estimates. So some of these difficulties you need to take into account, as I say, makes modelling of networks more challenging. Rebecca mentioned this iterative process. I'm just going to mention a few of the things that we need to consider that interact with each other. So vehicles, pedestrians interact, shared lanes, short lanes, unequal lane use. All of these are things to think about. Interdependence of signal timing and saturation flow rates. So if you change the signal timings, or the program changes the signal timings, that can affect the final estimate of saturation flow. You may, for these reasons, need to go back and do several iterations before you get that calibration and validation correct. So I think this is really, as I say, backing up some of the things Rebecca had said earlier. So we do need iterative methods to get that right. Now, I think that's taken me pretty much to the 20 minutes. So I'll thank you for your attention, and I'll pass back so we can hear from the next speaker. Thank you.
Thank you very much, Mark. Let me share my screen. So for our third presentation, I'm glad to introduce David N. David has been working with PTB Group since 2009. Previously, he was working with emerging consultants, being involved in different transport, master planning, and traffic simulation projects in Australia, Asia, and the Middle East. He is now mainly looking after customers and markets in Australia and New Zealand. He has also been involved in different ITS and MAS projects in Australia as well as Asia. So over to you, David.
Thank you very much for the introduction. Let me see if I can share my screen. Okay. Let me know if you can see it.
Yeah, perfect.
Perfect. So 1 second. Okay. Right. Okay. Thank you very much. I'm very delighted to be presenting today at the ITE ANZ seminar. So I'm going to talk about calibration and validation in microsimulation models. My presentation is broken down into 3 parts, starting with why calibration and validations are important. And then I will go into a little bit more detail on the driving behavior model, different parameters and settings, which you can adjust for calibration purpose. And then I'll talk about some of the tools that are available in the microsimulation packages, and also some of the more typical types of measurements that you can output from a simulation for calibration. First of all, the 2 points I want to make. Microsimulation model is agent-based, so it's different from Cedra or other deterministic solutions. So every agent has its own set of attributes. So yes, we're talking about traffic simulation. Every vehicle is an agent. So they all have different, for example, 3D models, desire speed distributions, acceleration profiles, deceleration profiles. So they all have different attributes. And the second point is there is a driving behavior set which agents follow. So, so in the diagram here, I'm trying to show the car following model. Probably it's not so obvious in the diagram, but I'll talk a little bit more about the model later. So yeah, so simulation is not just an animation. There is a sound proven scientific model behind the driving behavior in the simulation. And you can have more than one driving behavior sets if you want, if you need to. But the bottom line is that each agent has to have a driving behavior set associated with it. Now, combining the first 2 points, depending on the distribution of attributes that you have and the driving behavior sets, you may have different agent interaction and different simulation results. So just like in the diagram here, you may have different vehicle types like trucks, cars, light rail, you may even have buses and some other vehicle types. They all have different attributes, different dimensions, different speed, different acceleration, deceleration. They may even have different driving behavior sets as well. So depending on what attribute values and what driving behavior model parameter values that you are using, the interaction between themselves and also between the vehicles and the infrastructure, such as signals, could be different, which will then generate different simulation results. So that's why, well, the bottom line is that the simulation results are supposed to be replicating the observation, replicating the reality. So that's why it's important for us to go through this calibration process when you build a simulation model. So that's my definition. I think it's kind of similar to what Rebecca said in her presentation. So calibration is the adjustment of model parameters and attributes basically to reproduce the local driver behavior and traffic performance characteristics. So I'll talk a little bit more about the driving behavior model parameters. I'll focus more on that rather than the attributes of the agents. Okay, so maybe this is a little bit more specific to VSIM, but you have similar driving behavior model in other simulation packages like AIMSUN or others. But in VSIM, we have basically these 4 different submodels. Car following model, how cars or vehicles follow each other. A lane change model, how a vehicle is making a lane change. Lateral behavior, how vehicles are making, how they behave laterally on the road, and also how drivers would behave or react in front of a signal controller. So 4 different submodels, and they all have different parameters associated with these 4 submodels. And all these parameters are open for users. So users can actually look at these parameters to investigate them, to understand what they are, their impacts on the driving behavior, and also they're free to adjust them to make sure that the driving behavior in the simulation would replicate the observation. Now, with the emergence of new technologies, new behavior, new trends, we are also trying to improve our software to keep up with the changes and also to cater for new use cases as well. So for example, recently we have also introduced new standard driving behavior sets, driving behavior models for autonomous vehicles. So all these parameters are open, but there are default values assigned to these parameters for all the models. So where do these default values come from? So they're mostly coming from observations and real-world data. But please note that, with VSIM is developed in Germany, so most of the observations and real-world data are coming from Europe or from Germany. So in other words, if you don't change the default values in your driving behavior model, your simulation will probably be kind of similar to the driving behavior in Germany, which is probably not too dissimilar to the driving behavior in Australia or in New Zealand. But if you're from some other countries where the driving behavior is completely different, then you may really want to look into these parameter values and adjust them to make sure your simulation is well calibrated. Also, we derived some of the data, some of the values from research paper, and also from our participation in research project. So for example, we were involved in this project called Coexist, funded by the EU, and there were many partners in this project with car manufacturers, OEMs, different cities, other technology providers as well. So as the name suggests, the project is to look at autonomous vehicles to see how AV is going to be phased in to mix in with the conventional vehicles on the road network. So through this project, we're able to obtain a lot of data, and making use of the data, we're able to develop these basically three standard driving behavior sets for autonomous vehicles. I'm not going to go into all the models in detail. I'll just talk about the first one, the car following model. So we have a graph here. We have two vehicles, a blue vehicle and a red vehicle. Blue vehicle is behind the red vehicle. And the x-axis is the speed difference between the blue and the red vehicle. Y-axis is the distance between the blue and the red vehicle. So if the blue vehicle is going faster than the red vehicle, then the curve you'll see later on will be on the right-hand side of the graph. Then we have a safety distance between two vehicles. And if it's below the safety distance, then the blue vehicle would need to brake, or else there might be a collision. If it's beyond the safety distance, then it's free driving. Now, just imagine if you're in the blue vehicle, but you're going slightly faster than you're getting closer and closer to the red vehicle. And then when it reaches the safety distance, then you may need to do something, or else there'll be a collision. But what the car following model says is that even before reaching the safety distance, the blue vehicle will actually react before then. So that's a reaction threshold. So it will react before then, basically kind of registering there's a vehicle in front of him or her. And then the blue vehicle will start decelerating until it reaches the safety distance. And then at that point, it will then enter what we term as a vehicle following mode. So basically, it's kind of
we've come home to our dad about the problems that we had at school.
So in the car following, in the following mode, so that's when the blue vehicle is kind of unconsciously accelerating and decelerating, trying to maintain that safety distance from the red vehicle. So basically, that's the notion of the car following model, and we have all the different parameters associated with this model that are open to the users. So basically, those parameters are describing this curve, and they're all open to the users. So we have different parameters, like we have a parameter for safety distance, a parameter for the reaction threshold, a parameter for even for the extent of the oscillation during the following mode. So all these different parameters are open for users. They can adjust these parameter values accordingly to make sure that the car following behavior that they are simulating would be replicating the observation. And we have different parameters for other submodels as well. So we have different parameters for the lane changing model, for the lateral behavior, for signal control as well. So this is a snapshot of the car following model. So altogether, we have 10 different parameters. As you can see, they're all open for users to adjust them. And they are also described in detail in the manual, so you can actually check what they are for, what that effect would be if you change these values. Now I'm going to go into the different tools that are available in micro simulation packages, which will support you when you're calibrating your model. So matrix estimation is one of the more popular operations being used when it comes to calibration. I think Rebecca mentioned this before as well. So this is basically comparing the assignment flows with counts, and then adjustment or correction will then be made to the prior matrices. So that's available in basically in most of the modeling simulation packages. Flow bundle analysis is also a helpful tool when it comes to calibration. So in some other platform, it might be called a select link analysis. So basically you select a link, and then when you run the analysis, you'll be able to see where the flows are coming from and going to via that particular link that you've selected. So quite useful so that you can see where the origin and the destination of your flows are for that particular link that you've selected. Also, you're able to output different types of statistical outputs, for example, GH, which was mentioned by Rebecca, and other statistical measurements as well. For example, means of different attributes for your different runs, and also the corresponding standard deviations. There are also many different types of graphical tools, visualization tools that you can make use of, tap into for your calibration purpose. There are different charts and graphs that you can create within the software for your calibration. In the video that you're seeing, we have 5 different links, and there's a signal in the middle of each link. And here we are kind of testing different parameter values, 2 different parameter values under the car following model. And you can see that impact on the effective saturation flow rate. Okay, so that's a great visualization tool which will help you with your calibration. Now, when it comes to measurements, different types of measurement that you can output, turning volumes is one of the more popular one to be used. It's something quite easy to get on site, also very easy to output from a simulation, and also in many modeling guidelines, turning volumes or link volumes are being used for calibration. Similarly, many modeling guidelines, speed is also being mentioned to be used for calibration. And again, it's something quite easy to be obtained on site. You can get it from floating bar data or via data providers such as GoVision or data from Sky. And again, it really depends on the application, on the use cases. So if you have a freeway study, for example, okay, when speed is important, travel time is important, then you may want to use speed for your measurements. Or if you're doing a corridor study, then you may choose to use speed heat maps, you know, when it comes to calibration. So here we have two diagrams showing the heat maps, so basically it's showing the different speed at different sections of the corridor at different time periods. That's something that can be generated quite easily from the simulation. Sometimes you may also want to take a little bit deeper. Instead of just using speed, you may want to use speed profile. Again, it depends on the use case as well. So, for example, if you want to use a simulation for emission calculation, okay, emission analysis. So not only the speed, but also the acceleration, deceleration are quite important when it comes to the calculation of emission. So for that, you may want to use speed profile for your calibration. Again, that's something you can obtain quite easily on site, you know, using trajectory data, probe data, and something that you can output from a simulation. In BSIM, you can output that using vehicle record file. And then there's some other measurements as well. For example, travel times, delays, queues, all these have been mentioned by the 2 previous presenters. Yeah, so all these are pretty common measurements to be used for calibration. Now, I want to talk about some of the more common calibration variables to be used for different use cases. So if you want to use a simulation for signalized intersection analysis, you may want to use volumes, saturation flow, speeds, queue lengths, and delays for your calibration. On the right-hand side, these are all the different attributes or driving behavior model parameters that you can adjust for these different measurements or variables. Now, when it comes to corridor study, volumes, travel times, and also as we looked at just now, the speed heat maps for calibration.
What's going on, guys?
Okay, for freeway study, again, speed, volumes. Sometimes, you know, you may also want to pay attention to headways and standstill distances. So these are the parameters under the car following model. And then sometimes, you know, you may also want to investigate the parameters within the lane changing model as well, because here we're talking about freeway studies. So you may need to pay a bit more attention to the weaving, merging, diverging behavior. So lane changing submodel might be something that you need to pay a bit more attention to. Cooperative behavior, so that's also under the lane changing submodel as well. For urban road study volumes, as well as curbside activities. So here we talk about urban settings. So curbside activities such as parking maneuvers, loading bay activities, pickup drop-off activities. So all these different elements can also be incorporated into your traffic simulation. So we have different network objects and the associated attributes that you can look into. Speeds, of course, and then again, interactions with pedestrians and cyclists. So these are all the different elements that can also be incorporated in your traffic simulation. And here, because we're talking about urban road study, so in the city settings, so you may also want to pay a little bit more attention to signals as well, because most of the delays will be occurring at signals rather than mid-block. So these are just a sample of some of the applications and some of the suggested measurements that you can use. There are many other use cases as well. I can't talk about all of them now, but we are actually preparing our own modeling guideline, which with a more comprehensive list of use cases. So so that will be released when it's finalized. Hopefully this year. So that concludes my presentation. Thank you very much for your attention. Now I'll pass it back to Christian.
Thank you, David. Now, please feel free to drop your questions in the chat box. Now we're gonna pass through our Q&A session. So then we had a few questions in the chat. So the first one is, can we use the JCT app? I assume is from the JCT consultants to determine the saturation flow. I think that could be for Mark, maybe.
Yep, I'm happy to pick that up as a question. If you have a look at the JCT website or the app itself, you'll see that the way it works is that you're hitting a button when vehicles go, you're denoting the start of green, and also you're denoting the point at which the queue has discharged. Now, this is very similar to the SIDRA survey method I mentioned. Now, essentially, the SIDRA method, if you remember, I won't try and dig the slide out, but if you remembered what it showed in that diagram, we essentially assume that the saturation flow builds up from 0 to the sustained queue discharge rate over the first 10 seconds or so. Other methods like HCM, I think, assume that takes 3 or 4 vehicles, which is similar. And then that discharge rate is sustained until you reach the queue when the queue is discharged. So that looks like the JCT method is very similar. I won't say it's identical to SIDRA, but it would be very similar. And I think it would give you a good saturation flow value. With a little more detail, you might perhaps calibrate it slightly to give same results as SIDRA, but from what I can see, I would expect it would give a good saturation flow to work with. So yes, I would endorse the use of that. Thank you.
Thank you, Mark. I have one question. I think Rebecca and Mark mentioned about the iterative process of calibration and validation. So this iterative process is meant to be for the model construction. But what happens if you have to build a proposal, a model for a proposal? How do you validate this proposed model? So I mean, instead of the existing model.
Look, I'm happy to start with that one. The main thing is that by starting with something new, you have nothing to validate against. So for that purpose, there is no real validation process, and what you are doing is starting with a new baseline to develop net comparisons. What it is that you are then ultimately comparing multiple future year scenarios. So you do have to rely upon either past experience for local area parameters. You can still calibrate those for local driver behavior or things like that, but ultimately you're relying upon the base default parameters in each of the software packages. But if anyone else has a different view, go for it.
Look, I think I just endorse that. I mean, this sort of locks into a question about how reliable are the default values in SIDRA, which is a good question. We've based those on Austroads and past surveys. Many sources have come together over many years to arrive at those defaults, but they are defaults. They're not perfect. As time goes on, of course, things may change. We try to update those from time to time. I know in the presentation mentioned the autonomous vehicles. We don't know what that's going to do to things like gap acceptance and saturation flow. Some people think it might be better. Some people think it might be worse. So as time goes on, we need to keep looking at the defaults, but what are in there at the moment we think are pretty good. And that's probably the best you can do if the intersection doesn't exist yet.
I think if it's
Okay.
a completely new proposal with then probably I think in my experience, probably you might find a similar site for calibration purpose. We've done that before. Regarding default values, so the default values in the software are all calibrated. I should say they're more calibrated, based on, kind of European and German behavior. So if you use those default values to start with, let's say, then probably that will give you a more, I would say, a conservative driving behavior, which is probably kind of like the worst case scenario. So probably that might be a good starting point, and then you can start, fine tuning the behaviors and introduce later on. Yeah.
Okay, thank you very much. We have a question in the chat for David. Can the car following models allow for looking not just at the vehicle immediately in front, but say those 2 or 3 vehicles in front?
Yes, you can. That was only a very simplistic representation of the car following model. I'm just using 2 vehicles. But yes, in the car following model, there are parameters that you can adjust you can adjust how many vehicles or how many objects that the agent will observe closely in the car following model. So when I say objects, I'm not just talking about vehicles, but also other objects like signals, different giveaway signs. So these are what we term as objects. So you can actually calibrate. You can actually change the number of objects that the agent would observe. So it's not just one vehicle.
Okay.
Yeah.
I have one question. In addition to the first one that I asked, is it possible if we don't have survey data to validate or the model, we can use historical data from similar areas or from that area in a specific to calibrate the model? So
I don't know who wants to pick this up. We're hesitant with that. I mean, look, admittedly, if we talk about saturation flow surveys that were done over a large number of intersections over time, so you perhaps saying that we've looked at similar intersections, but I think there are some pitfalls in just looking at something and assuming that it'll be similar. But I guess if you can't do any better than that, maybe that's a basis, but always question what you're using and question the defaults too. If you think a default value doesn't make sense, question it. Ask us why are you using X as a value? And also, just as a general thing about defaults, at least from a SIDRA point of view, there's defaults for everything, but make sure you put in the things you know. Even if you haven't built an intersection yet, you know how wide the lanes are going to be. Don't use the default lane width, and you know what the gradient's going to be. Don't use the default of it being level. So put in everything you can and rely on the defaults for the things you don't know. But I'll open this to others to comment further.
Yeah, I mean, if you really don't have the data and you have to use a similar site, yeah, I would just be a little bit careful, because I'm talking about micro simulation. So the behavior could be different, even within the same site. Even for the same site, the behavior might be different at different times of the day. Even different locality. If you talk about driving behavior within the CBD compared to the driving behavior in the suburban setting, so that could be different. So yeah, so these are all the little differences that you would need to pay a little bit of attention if you really have to use what you term as a similar site, for your calibration purpose. Yeah.
I agree with both, and so I'd just say that the approach more from a consulting perspective is always, in that case, just to look at what is a net difference assessment when you move forward. So even if you do need to adopt base parameters, whatever you're doing, you adopt the like-for-like comparison. So there's a couple of things that we always do, which is apply a little bit of a sensitivity test. So allowing in the likes of Sidra or Lensic to calculate a default cycle length. Historically, modelers will understand and learn what the road network agencies consider as reasonable cycle lengths for a particular location or environment. So from those sorts of things, that is something you can potentially calibrate based on conditions to an element of realism and understanding. But beyond that, I agree, it's a little bit limited with what you can do.
Okay. Thank you very much. We have another question in the chat. When it comes to route choice calibration, I believe the general practice is pretty much limited to using travel time as the sole variable to estimate generalized costs. So what do you think about utilizing more variables like cost per kilometer, perception costs, to make route choice a bit more contextual?
Yes, for sure. Positive. In fact, in VSIM, we do have these parameters that you can use when it comes to calibrating your route choice in a dynamic assignment. So I think we actually have 3 different types of cost that you can adjust. So definitely cost per kilometer, and I can't remember off the top of my head, but I think there's a general cost as well, and there's a third one I can't remember. So yes, there are functions which support this type of calibration in the micro simulation model. Yeah.
Okay. We have another question. What do we do when we do not have SCADS data and the models were received from council which had traffic data pre-COVID period, for example?
Look, I'll start on this one. Without SCADS data, certainly in Sidra, you can get Sidra to estimate the signal timings and in fact, we'd prefer you use the Sidra saturation flow defaults than trying to base saturation flows on MF estimates because of the way the timings come in, particularly if you're getting Sidra to estimate the timings, they may not be the same as the SCADS timings anyway. So Sidra can do a pretty good job without SCADS data. That's not to say that you shouldn't account for your model being part of a SCADS system in the future. So you might know that it's going to run on a fixed cycle time as part of a network. If it's a lightly trafficked intersection, Sidra might come up with a 60-second cycle time, but if you know it's going to be connected up into a network that might be ridiculously short, it might be operating over 100. So you can force those sort of cycle times. You could perhaps estimate from other coordinated intersections, what type of cycle time might run. I don't see that as a big problem. The COVID one is interesting. Look, it's anyone's guess about what is going to happen from now forward. We're seeing people using cars more and public transport less. Is that going to regress back to how it was in 2019? You know, obviously a lot of people hope so, but it's a guess as to where things are going to go. The hope I would have is that in the longer term, traffic would probably go back to similar patterns to what we had seen, but obviously growth is going to be there anyway, and estimates of growth are always difficult. You know, we try to work out how an intersection is going to work in 10 or 20 years' time. We probably always made fairly rough assumptions about growth. I would hope that in that context, the COVID is really a small blip, but I'll pass it to others for any comments about that.
Look, from a perspective of the modelling we're doing from consultancy side at the moment, a lot of it, when we're talking about SCATS data, I'm not sure if you're particularly after signal timings, but historic traffic volumes along the areas, we do have, as well as the fact that SCATS detect account data is often available as open source data or for small costs. There's a lot of other road authorities that have got permanent data stations set up, and you can access open source data for those. So in the past, we've been looking at historic for the last, say, 3 years, volumes on a road in a particular month over the last 3 years, and just drawing a comparison of whether post-COVID volumes are in the same order of magnitude. Now, we're never going to be exact, but at least if we can see that we're sitting up higher or lower, we can make estimates and potentially uplift whatever data source you do have. So that's sort of the feedback I've got on that.
Yeah, not really further comment from myself. Yeah, I mean there are other data sources that that consultants can tap into. There are a lot of data you can get from data providers, both actually historical as well as real-time data. So that might be another source that they can tap into if they don't have the SCATS data. Yeah.
Okay. I think this would be our last question, and it's more general question. Do you have any suggestions or best practices on how to deal with the overfitting to the observed data that could occur as the result of the calibration process?
Yeah, that's a difficult one because you know, there's always room for improvement. But you know, at the same time, you know, it's an investment. You know, the more effort you put into this to the calibration, you know, that's this yeah, it's a balance that you need to strike. You know, I would say you know, I'm talking about microsimulation. You know, there's so many different parameters, attributes that you can look into. Okay, but I think it really depends on the use cases or the applications that you're using the simulation for. And if you, for example, if you're doing freeway study, you know, travel time is very, very important. Then maybe you just be focusing on travel time, speed, because that's the most important measurements that you want to get right. So I think really, I think it comes down to, for me, you know, what the model is for, what the objectives is, and then calibrate the model accordingly based on the objectives. Yeah.
Okay, Mark, Rebecca, do you want to add something to it?
It's a difficult one. Yeah. I mean, it probably comes down to how much reliance you want to put on your observations. If you're say looking at queue lengths, did you survey queues over a long period? How long was your observations? Did you work out an average queue that included every observation? I would think that there's good reliability there, and it's worth fitting to that, whereas perhaps a percentile, like a 95th percentile queue, might have only occurred once or twice in the hour, and that's more difficult. And I'll also come back to what I said about making sure you've still got sensible inputs to fit the data. You say, oh yes, I fitted this exactly with a saturation flow of 3,700 and whatever, and I think, well, no, that wasn't a good thing to do. I don't know if Rebecca wants to add any.
I think just on that, my last comment just comes back to understanding what is the purpose of the modelling, and also then what you're going to do with the model beyond just the base calibration. So I've had scenarios where, and Mark alluded to it, where you can produce the best calibrated model, but because you've had to change so many parameters, the flexibility for that model to reflect road network changes or things like that is actually limited because you've almost locked in too many. So it's always important just to keep an understanding of what you're going to do with it and validate what are the key parameters for that that'll demonstrate net difference for the client. So.
Okay. Well, I think we don't have time for more questions. Thank you very much. Please please complete the 2 minutes post webinar survey that is in the chat box. And I want to thank Mark, Rebecca, and David to take your time to be here and share with us your experience in calibration and validation of micromodels. Thank you very much.
And
Thank you.
Thanks everyone. Thanks to the audience who've spent their time
Yeah, thanks.
listening to us, and that's well worthwhile.